Hello good people, I'm going to talk about the 4 fundamental forces. Yes, it is that time already. We are about to wade into physics. So pull up your socks and put on your tall gumboots. Despite what the Jedi might tell you, there are 4 fundamental forces that govern the universe. Here they are. We have the strong force, the electromagnetic force, the weak force, and the gravitational force. I'm going to give a relatively quick overview of each, and I'm going to start with the weakest of all of them, which, contrary to the names, is not the weak force, but the gravitational force. The gravitational force is indeed the weakest, but it works over long distances, and it depends on mass. In terms of day-to-day life, gravitational force is perhaps the one that we are most familiar with. It is the reason why we stick to the Earth and do not float about. It is also why the Earth revolves around the Sun and why the Sun revolves around the center of the Milky Way galaxy. So yes, it does work over very long distances. However, it only truly comes into play when we are dealing with objects with huge masses, such as stars and planets. Truth be told, gravitational force exists between any two objects that have a mass. So when you stand next to somebody, yes, there is a gravitational force between the two of you, but it is negligible. So much so that you do not even feel it. The gravitational force between two objects can be expressed with a relatively simple formula. F, the force, equals capital G, which is the gravitational constant of the universe, multiplied by mass of one object multiplied by mass of the second object, divided by the square of the distance between the two objects. The value of capital G, the gravitational constant, is a very tiny number. It is 6.67 multiplied by 10 to the 11. And the unit is Newton meter squared over kilogram squared. You do not necessarily need to worry about the unit at this stage. However, what you should appreciate is that the gravitational constant is indeed this very tiny number. It is also the reason why gravitational force only comes into play when we have huge masses that will offset this tiny gravitational constant. All right, let's move on to the weak force. The weak force enables a nucleon change. What does that mean? Nucleons are particles within the nucleus, so protons and neutrons. Let me write the symbols for those two. So here we have a proton, and next to it we have a neutron. The weak force allows for a proton to be changed into a neutron and for a neutron to be changed into a proton. For example, I'm going to start with a carbon-14. So its atomic mass number is 14 and its atomic number is 6, representing the 6 protons in the nucleus. Now suppose that one of the neutrons inside the nucleus changes to a proton. That means we would now have 7 protons and therefore a nitrogen. The atomic mass number, protons and neutrons, still remains the same, 14. When this happens, we are also going to liberate an electron as well as an anti-electron neutrino. I did warn you, we are wading into physics. Luckily though, you do not have to worry about neutrinos. At this stage, you just need to appreciate that due to the weak force, occasionally a neutron might become a proton. But it can go the other way around. A proton could become a neutron. So let's say I have a different type of carbon, carbon-10. And now imagine that one of the protons becomes a neutron. This means that now we have 5 protons and therefore boron. The atomic mass number is still 10, protons and neutrons combined. For completeness sake, when this happens, we are also going to liberate a positron as well as a neutrino. Again, you do not have to worry about positrons or neutrinos. Now, even though this force is called the weak force, it is 10 to the power of 25 times the gravitational force. However, it only applies to extremely short distances. We are talking about the size of a proton. Let's move on to the electromagnetic force. Within chemistry, we often refer to this as the electrostatic force. It is responsible for the attractive and repulsive force between charges. What does that mean? Let me bring in a few charged particles. The two positively charged particles at the top will repel each other, whereas the positive charge and the negative charge at the bottom will be attracted to each other. The electromagnetic force is about 10 to the 36 times stronger than the gravitational force. And it can be expressed by yet another elegant formula. F for force equals Coulomb's constant K subscript E multiplied by value of charge of one particle multiplied by value of charge of the second particle all over the square distance between the particles. The value of the Coulomb's constant is a very large number. It is approximately 8.99 multiplied by 10 to the power of 9. The unit is Newton meter squared over the electric charge squared. Capital C stands for Coulomb and it is the unit for electric charge. At this stage, you do not need to worry about these units. However, you should appreciate that the Coulomb's constant is a very large number, especially when you compare it to the gravitational constant. And this is why the electromagnetic force is so much stronger than the gravitational force. So why are we not experiencing the electromagnetic force on a daily basis the way we experience the gravitational force? Just like gravity, the electromagnetic force actually does work over long distances. However, most macro objects or large objects, such as humans, goats, planets and even stars, do not have a charge. Large objects are overall neutral. And so large objects tend not to experience the attractive or repulsive effect of the electromagnetic force. On the other hand, when we get down to the atomic scale, where we actually have charged particles, the electromagnetic force comes into play and is in fact responsible for most of the chemistry that we see around us. The more observant may have noticed that the formula for the electromagnetic force and the formula for the gravitational force are rather similar. The setup is identical. Conceptually, there are two main differences. The first one stems from the fact that, as pointed out, the gravitational constant is a tiny number, whereas the Coulomb constant is a huge number. And the second difference comes from the fact that while we can only have one type of mass, we can actually have two types of charge, positive and negative. This is also why when we talk about the gravitational force, we only talk about the attractive nature of the gravitational force. Two masses will attract each other. On the other hand, when we talk about the electromagnetic force, because we do have two different types of charges, we can have an attractive force and a repulsive force. All right, let's move on to the strong force. The strong force is about 10 to the power of 38 times stronger than the gravitational force. Or to put it another way around, and with respect to the electromagnetic force, it is 100 times stronger than the electromagnetic force. The strong force works over very short distances, think size of a proton, and it is responsible for keeping the nucleus together. What do I mean by that? Let me draw in a nucleus of a helium atom. A helium atom has two protons, represented by these two red spheres, and it also has two neutrons in its nucleus, represented by these two purple spheres. The neutrons are neutral, while the protons are positive. Considering what I have just said about electromagnetic forces and how like charges repel, this actually looks a little bit odd. Why are these two protons sticking so close to each other? Why are they not flying apart? Well, the answer is the strong force. You can think of it as the glue that keeps the protons and neutrons together in the nucleus. And because it is 100 times stronger than the electromagnetic force, it is able to overcome the repulsive force of two like charges. So once again, it is the strong force that keeps the nucleus together. The fact that the strong force works only over very short distances means that there is an upper limit to the number of protons that we can have within the nucleus before the nucleus becomes unstable. Our current understanding of physics tells us that after about 83 protons, the nuclei become unstable. And this is why we end up with radioactive elements. In essence, radioactive elements are elements whose nuclei are not stable. In summary, there are four fundamental forces at work in the universe. The gravitational force, which keeps us stuck on Earth, the weak force, which allows for a change from a proton to a neutron and vice versa, the electromagnetic force that is responsible for attraction and repulsion between charged particles, and finally the strong force, which is responsible for keeping the nucleus of an atom together. These strong and weak forces work over very small distances. The gravitational force depends on mass and can work over large distances, and the electromagnetic force is the one that is responsible for most of the chemistry that we see around us. To those who are right now preventing their brains from escaping through their ears, I can say two things. Firstly, aren't you happy that you are not doing physics? And secondly, that is all for now, and I will see you on the flip side.